Hey guys, welcome back. In the last few lessons, we were looking at two important file formats, RC file and ARC. In this lesson, we'll learn about another file format, Parquet. We learned what is RC file and we learned what is ARC, and how ARC is better when compared with RC file, and how ARC achieves the efficiency and the performance benefits that it claims behind the scenes. So what is Parquet and why do we need another file format? To answer the question, let's talk about Parquet's background and the motivations behind Parquet. Parquet is again a columnar file format, very similar to Arc, and it was born out of a joint effort between Twitter and Cloudera. Parquet was built around the same time when Hortonworks was working on building Arc. Both development teams from Cloudera and Hortonworks did not have much transparency what each other were working on, at least during the initial days. And we ended up with two file formats designed to serve very similar purposes. Okay, let's now look at what is Parquet. Parquet is a columnar format similar to RC file and ARC. The records are first horizontally partitioned, and then the data is stored in columnar fashion in row groups. The row group size is big in Parquet when compared to the 4 MB row group size in RC file. Parquet recommends the row group size to be closer to the block size to take advantage of sequential reads and data locality. We have seen customers using Parquet with row group size of 128 MB and even 256 MB in many instances. We will see the file structure of Parquet in a bit. Parquet does very similar and efficient encoding and compression like ARC. As in ARC, Parquet does look at the type of data stored in each column and encode efficiently. It also uses dictionary encoding like ARC. Each column is compressed at the column level. Initial version of Parquet did not support any indexes, but later version of Parquet does support indexes and store minimum and maximum statistics for each columns. So far, nothing special about Parquet, correct? So what is Parquet's specialty? When you hear someone talk about Parquet's features, especially from Cloudera or from Twitter, you will immediately hear that Parquet is built for anyone to use and Parquet does not play favorites. What they mean by that is, Parquet is designed to work with any tools like Pig, Hive, MapReduce, Spark, etc. That means that a file format like ARC cannot work with other tools? That is not true. ARC can work with many tools like Hive, Pig, Spark, etc. However, RC file and ARC were designed initially to work with Hive and later integrated with other tools. It is true, Parquet was from the get-go designed to work with many tools, but this point is not a differentiating factor anymore for Parquet, as ARC can integrate well with many tools outside of Hive, and Hortonworks is the driving force behind ARC. There is one area Parquet really excels, and that is handling complex nested data. And that is the main reason Twitter got involved with Parquet. Twitter, behind the scenes and in its API offering, uses complex, nested JSON-like messages to represent tweets and other metadata information about the tweet. Messages, something very similar to what you see on the screen. Let's say you have records in the format or schema as it is shown on the left. Our data has information about an employee, his phone number, and his subordinate's name and their phone numbers. In the right, we have sample data based on the schema on the left. We have an employee named John with a phone number and two subordinates, Steve and Jerry, and their phone numbers. We have another employee named Emily with no subordinates. Now, how do you represent this data in a Hive table? We don't need any special file format to store this sort of information. We can use Hive's inbuilt complex data types like struct, map, array, etc. to represent this structure. To know more about complex types, check out the Twitter lessons under Hive chapter. Here is how we can represent the schema in Hive. Employee becomes a struct, which will have three elements: employee name, employee phone numbers, and subordinate. An employee can have multiple phone numbers, so employee phone numbers is an array of string values. Pretty straightforward, right? An employee can have multiple subordinates, and we need to record the subordinate's name and phone number. Since an employee can have multiple subordinates, we'll have subordinate as an array. Next, we'll use a struct to store subordinate's name and phone number. So subordinate becomes an array of struct, and subordinate is inside employee struct. That's multiple levels deep. So we are able to represent nested data in Hive, but the question then becomes, how does this complex nested data get stored in columnar fashion? If you take our stocks table and if you would like to store it in columnar format, column values from individual columns are stored together. That is, exchange values across all rows are stored together, symbol values across all rows are stored together, so on and so forth. Now, in our previous slide, we were showing only 2 employees. Now, imagine millions of records in our data set with nested data. How do we turn this data or records into columnar fashion? Confused? Okay, let's visualize these two records in a table format, which makes it easier to understand the problem better. In the first record, we have an employee named John and his phone number. John has two subordinates, Steve and Jerry. Steve has a contact number and Jerry does not. There are a couple of things to note here. First, subordinates could have multiple values, and second, phone number under subordinate can have empty or null values. In the second record, we have an employee named Emily and her phone number. Emily is not a manager, so she does not have any subordinates. From this, we can see that subordinates is an optional data element. How do we take this table, which is in row major format, and convert to a column major format? A typical table, like our regular stocks table, will have row by row information with allowed null values for certain columns. So to turn a table into a column store is simple. Just group the column values together and that is it. To convert the table that we see here, employees, into a column format will end up storing employee name column values together, employee phone number column values together, and also subordinate name column values together and subordinate phone number column values together. That is, we'll treat each of the data point in our nested data as a column. But there are few challenges. When we deal with flat, non-nested data, for example, our stocks data set, for any given column, we either have a value or we don't have a value, meaning it could be null. That is it. But the real challenge in storing nested data like we see here is a column could be null, meaning it is an optional column. If it has value, it could have multiple values or repetitions for the same record. For example, from record 1, we know subordinate can have multiple values for a given record. Finally, column values could be nested. That is, to reach subordinate name, we have to go through employee, and then the subordinate, and then reach subordinate name. So column values could be nested. So we need an efficient way to identify optional or null values along with repetitions and nesting in column values. Why this is important? When we store nested data in columnar format, it is important to know the repetitions and nesting because when it is time to reconstruct the record as a whole, we know how to efficiently pull out individual column values and construct the record. Also, if we are reading just values from one column, it is easier to position the column values in the schema. Or in other words, we can easily identify where the column values will go in the schema. Arc's idea was to flat the nested schema and group column values together. It is straightforward, but it is not very efficient. And Arc struggles to handle nested data which is complex with multiple levels of nesting and frequent repetitions. Google had an efficient way to address this problem, and in 2010, they published a paper named Dremel to show how they work with complex nested data. Parquet borrowed concepts from the Dremel paper and implemented the record shredding and assembly algorithm from the paper to handle complex nested data. Dremel paper from Google showcased an algorithm named record shredding and assembly that store two pieces of information along with column values, definition level and repetition level. These two values, when stored along with column value, will help identify the position of the column no matter how deep the nesting is or the number of repetitions in the nested data. Let's now see what is the definition and repetition level values for each subordinate phone number column for each record in our sample employee data. I know what you're thinking. Before we can plot the definition and repetition levels, we need to know what is definition level and what is repetition level. It is a fair point. Let's first understand what a definition level is. In our schema, let's say employee is the topmost level and it is at level 0. Employee name, employee phone numbers, and subordinate are at the next level at level 1. Finally, we have level 2, which is subordinate's name and subordinate's phone number. When a column is null, definition level helps in determining whether it is just the column value that is null or the column's parent itself is null, which in turn makes the column to be null. For example, take the subordinate's phone number column for record 1. We have null for phone number, meaning we don't have the phone number for Jerry. Now take record 2. The phone number in subordinates is null, not because the phone number is null, but because there are no subordinates for Emily, and the subordinate itself is null. We need a way to differentiate when a column value is null. Is it null because the column value itself is null, or is it null because its parent is null, which makes the column value to be null? This is where definition level comes in play. Definition level records the level at which the value for a column is last defined. Let's plot the definition level for subordinate's phone number for each record and it will make more sense. For subordinate Steve, the phone number is defined and hence the definition level will be 2 because by definition that is the level we have the phone number defined. Now let's plot the definition level for subordinate Jerry. We don't have a phone number for Jerry, so what is the definition level now? The definition level is the level at which the value for a column is last defined. So the definition level cannot be 2 because phone number is not defined. So let's go up a level. We have subordinate and subordinate is defined. So definition level is 1. Let's now look at the second record. Phone number under subordinate is again null. But there is a difference between this null value and the null value for Jerry. The subordinate phone number for the record Emily is null because the subordinate itself is not defined or null, as opposed to Jerry's phone number where the subordinate is defined. So what is the definition level for the phone number under subordinate for the second record? Again, definition level is the level at which the value for a column is last defined. So for the subordinate's phone number in the second record, the definition level can be 2 because the phone number is not defined. It can be 1 because the subordinate is not defined. So it has to be 0. Parquet will record definition level for every column value for every single record in the dataset. That is, each employee name, each employee phone number, each subordinate name and their phone number will have a definition level defined. Now that we know how to plot the definition level, let's see how we can plot the repetition level. Before that, let's understand what is repetition level. Repetition level is the level at which the value is repeated. Again, let's plot the repetition level for subordinate's phone number. So what is the repetition level for Steve's phone number? Take a moment and answer. Are you saying the repetition level for Steve's phone number is 2? It is actually 0. Why 0? Because Steve's phone number is not a repetition. It is the first occurrence and hence it is 0. What is the repetition level for Jerry's phone number? Even though the value is null, we'll still need a repetition level. The repetition level is 1 because it is repeated at level 1. That is at the subordinate level. It is important to note that you're not recording the number of times a column value is repeated, but rather you're recording at which level the value is repeated. Even though Emily has no subordinates, we still have to record the repetition level for the null value. It is not a repeated value, but a new value, so the repetition level is 0. What we are showing here is the definition and repetition level for the phone number under subordinates. But the idea is to store the levels for each of the value across all columns and across all records. The goal is just to look at the column value along with definition and repetition level, and we can clearly identify where the column will be placed in the schema, irrespective of the repetitions and nesting involved. But do we have to know this much detail of what happens behind the scenes? Of course not. Google's Dremel paper described how their query system handled complex and nested data, and Parquet implemented the same to handle complex and nested data. We went over the implementation for those who are intrigued how Parquet and Dremel handle complex and nested data behind the scenes. But in reality, you don't have to worry too much about the implementation, as Parquet takes care of it for you when you store the data using Parquet file format. Now that we understand how nested and complex data is handled in Parquet, let's look at the file structure of Parquet. A Parquet file is made up of row groups, that is, horizontal grouping of rows. Within each row group, we have column chunks. If we have 5 columns in our table, we'll have 5 column chunks inside each row group. Inside each column chunk, we have several pages. Inside a page, Parquet will store the actual compressed column values. When we store a Parquet file in HDFS, as usual, it will be divided into blocks, and the blocks will be stored across data nodes. Parquet does compress column values and does efficient encoding like ARC as well. Now we know what is Parquet, how Parquet handles complex nested data, and we also seen the internal file structure of Parquet. At this time, you probably guessed how to create a Parquet table in Hive. So we don't have a dedicated session for that. And all it takes to create a Hive table to deal with Parquet file format is to just say stored as Parquet, and that is it. Loading a Parquet table is very similar to loading an ARC table or a RC file table. I know you're probably dying to know, given a choice, should you use Parquet or ARC as file format? Before we compare ARC and Parquet, let's touch on RC file. RC file was a great start as a file format, but it is replaced. So if you're thinking of using RC file, you should stop that thought and use ARC or Parquet instead. ARC and Parquet were developed around the same time in isolation to solve very similar problem. Both ARC and Parquet are light in terms of documentation. However, ARC documentation is slightly better than Parquet. When you listen to someone from Cloudera giving a talk on Parquet, you will certainly see them showing graphs that Parquet is better than ARC in terms of speed and storage. Similarly, when you listen to someone from Hortonworks giving a talk on ARC, you'll see them showing graphs that ARC is better than Parquet in terms of speed and storage. Even though ARC is from Hortonworks and Parquet is from Cloudera, both ARC and Parquet are included in both distributions. From our experience, it is very common for a customer who is using Hortonworks distribution to use ARC, and a customer who is using Cloudera's distribution to choose Parquet. The reason is, from the support standpoint, you'll get better support for ARC from Hortonworks and better support from Cloudera for Parquet. To be honest, there is no straightforward way to say whether you should choose ARC or Parquet. If you have simple row-by-row data and doing a lot of aggregations, filtering, etc., ARC will do the job just fine. If you have nested data like what we saw in this lesson, Parquet will work better. We would highly recommend you experiment with both ARC and Parquet to see which one works better for your use case at hand. With that, let's wrap this lesson. See you in the next lesson.